Welcome, public inventors.
Hello everybody, this is Robert L. Reed for Public Invention. I am most of Public Invention right now, so that organization is really just one person. What I would like to do today is to talk about the GlussBot, which I've been working on for over a year. I know Tony Stark would have completed this in his coffee break, but it's taken me a long time to do it. I have other videos which shows it walking and performing other poses, but this is a video to talk about the various components. As you can perhaps see, it is made out of Actuonics actuators, which used to be called Fergelli actuators, and these have built into them a linear potentiometer so that it can tell you where it is in its position. That's why each of these requires 5 wires. Inside here, as I hope you can see, I have a controller board which allows 6 Actuonics actuators to be controlled by a single PCB board, which is actually a Arduino Mega shield. So I'm now going to pop the cover off this, if I can do it without hurting anything. It's actually on right now. And here you can see the system I designed to allow 6 systems to be plugged in there. Most of the plastic that you're seeing here I 3D printed on my LULZBOT TAS 5 3D printer. This is a PCB board which I designed myself. I'm a beginning electrical engineer. I'm an expert computer programmer, but I'm a beginning electrical engineer. That board is available at Osh Park as a shared project if you would like to do it, if you would like to use it in some way. As you can probably see from the system here, if I can get it out, it has soldered onto it 3 motor controllers, dual channel motor controllers, which allows it to control up to 6 actuators. I'll show a close-up of that in just a minute. And it has a SparkFun Blue Smurf Gold Bluetooth controller. And so electronically, the system consists of 3 of these controller modules, each connected to 6 actuators for a total of 18 actuators altogether in Arduino Megas. And to my Macintosh computer over there, it looks like 3 Bluetooth devices. And I have an open source software program which happens to be an eLisp or Emacs Lisp program for making a connection to all of the Bluetooth monitors and controlling them into various poses. I 3D printed these cases, and originally I had a separate case for the battery pack like this and the Arduino controller board, but I decided it made it simpler to print them together. Here is an example. Here's the 12-volt battery pack. It's nickel metal hydride, and the Arduino control system. And of course, I 3D printed some little vent holes and everything so it doesn't get too hot. As always, engineering always progresses rather iteratively. I used to bolt things to the end of the Actuonics actuator, but I have since learned that I could unscrew the end piece it came with and print my own threaded parts. And it's a little difficult to get a 3D printed system to produce accurate threads, but with practice you can do it. I had to tweak this a little bit, starting with an OpenSCAD module, an open source system for making threaded components. And now, as you can see, I can thread these things directly in there. My previous joint is what I call the turret joint, which an example of which is here. And I'll talk about that a little bit later. That's a purely mechanical joint. But for the Wichita Mini Maker Faire, I tried to use this magnetic joint, which was an idea of my friend Robert Gatliff, who suggested that I attempt this, and it works. And the basic way it works is you put a 1" by 1/2 inch rare earth magnet in here, and it clicks together really nicely. The beauty of that system is that it's very easy to take it apart and then just snap it back together when you want to transport it. So the idea is that such a robot could be assembled very easily in the field. However, although the pull forces of these magnets and these hollow steel balls, which I get from King Architectural Materials or King Architectural Metals, is strong enough to support the 11 pounds that the Actuonics actuators can support. So in principle, it will never fall apart. Like any magnet contact system, it can be easily broken by side forces. And since the next version of my system is to try to climb up stairs, which is going to press sideways on the things, I'm going to go back to the turret joint system, which I have discussed in other videos, to do that. Now, I'd like to point out that for this application, I found the LULZBOT's ability to print in the material nylon has been extremely helpful, because these nylon components are so tough they almost never break. With the ABS and PLA parts, which I have printed, they often crack, and you can even see little cracks in my cases here where things didn't print quite correctly. But nylon has the property of toughness. It bends a little bit, and it's almost unbreakable. And so for this application, it's a wonderful material, and I plan to make a modification to use this sort of an adapter without the magnet stuff here and have it screw directly in there, and that should make for a very compact and strong joint. So as I said, I use nickel metal hydride rechargeable batteries in a little pack like this, and I solder my own pigtails on here so that I can plug them into the Arduino. The reason I use these batteries, which seem to last a really long time for my application rather than lithium ion, is that weight is not particularly important in this application. In fact, the strength of the system is actually one of its great advantages. These Fergelli or Actuonics actuators can exert about 11 pounds of force, and they only weigh, I think, maybe 300 grams or something. They're very, very light and very powerful. So right now, by far, the steel balls and the magnets are the heaviest part of this robot. Now, if you've seen my videos, you've seen it locomoting, that is moving around, and it's very important for the intended application that it be able to move. But of course, motion itself is not the purpose of the GlussBot. The purpose is to be sort of a telepathically controlled material that can assume any shape. So the purpose is to get into position and then exert force or withstand force in the environment, not necessarily to be extremely good at moving. This will never compete with a wheeled robot in terms of moving, but it is very likely to be far better at holding something up, because as you can see, it's completely omnitriangulated, made out of tetrahedra, so it's an inherently rigid and stiff system. In fact, there's a tiny bit of backlash possible in these actuators. If you push on them hard enough, you can drive them backward. But in general, if you take the power off, it simply becomes a rigid machine. And in a larger application, we could, of course, make a bolt here to bolt it into place, and then it would truly be a physical structure that is like a truss, which is why I call it the Gluss, which is a combination of the words slug, glass, and truss, because it's a truss, but it oozes around like a slug. I'm happy to say I demoed this at the Wichita Mini Maker Fair, and although the purpose is not to please children, children really enjoyed it, which I got a kick out of it. And also some serious engineers who were there seemed to think that it was a good idea. Okay, so I've taken out the PCB board Arduino Mega Complex. I hope you guys can see it, and you can see here that I have a little place to plug in all 6 of the the Actuonics actuators. Here I've soldered to the board 3 motor controllers. These cost about $5 a piece. The Mega is fairly expensive. I think it costs 45 bucks. The boards, I'm happy to say, are not terribly expensive. I had excellent service from Oshpark. I designed this board myself. This is an open source board that you can use, and basically I hand solder in all the headers and everything to turn it into a shield for the Arduino Mega. And I would like to thank the people who made this available via Creative Commons. In fact, this footprint started out as a SparkFun Mega Shield thing. I, of course, have modified it as is legal for me to do with the Creative Commons license. And, of course, you are free to do the same thing, and you don't have to pay anything for it. You have to pay Oshpark if you want the physical board, but their prices are quite reasonable. I think it's $45 for 3 of these boards, which to me, for robotics, is pretty good value. And of course, it fits on the Arduino Mega. I need to use the Arduino Mega because I have an extraordinary number of pins to try to control 6 motors at the same time. There are other ways of solving that problem, such as using a serial-based communication to the things, but I have found this to be reasonable for me. So this module, which fits into the 3D printed case which I made here, has been a good solution for me. Obviously, all of you who are mechanical or electrical engineers will immediately look at this and say, well, it can be packaged better, and it could be made much smaller, and so forth. And of course, you're right. This is an iterative work, and I welcome your involvement. All of Public Invention is a completely open source system. Nobody has so far assisted me very much, but I invite your help. I need artists, philosophers, electrical engineers, computer programmers. It would be nice to have someone help me make better videos than I'm making right now. In short, there's a lot of room to work on this, the GlussBot project, which I personally view as a serious research project. Thank you very much.